Okay, so in this video we're going to talk about Kepler's laws in a minute, but first I need to set the setting for this, and the first thing I'm going to think about is that I'm using alpha in this page, alpha and beta, for two curves or paths in R3. So that is, the input of these functions is a number, and the output is a vector in R3. So where I'm thinking about the I is a closed interval AB. So that means that both of these are curves that whose image is in, so it could be your beta, this would be your alpha images, curves in R3. So for every time you have these curves, at each t value you have a possible position alpha of t and a position beta of t. And it makes sense to take the dot product of those two position vectors. So this is the first one. And it makes sense to take the cross product of those position vectors. So what I'm saying here is that these two new operations are also differentiable. And not only that, but they follow the product rule, as in Calc 1, that it's the derivative of one of them dot the other plus the derivative of the other dot the first one. And the cross product is the same. So derivative of the first cross beta, and then plus derivative of the second cross alpha. So we're going to use that in a minute. The other thing I want to talk about first is that a little thing that we're going to use is that if you have a curve, now I'm calling it gamma, a curve in R3 of constant magnitude, and the derivative of that gamma is not zero, then you can guarantee that the position vector is always perpendicular to the velocity vector, or gamma prime. The way to prove this one is pretty straightforward. If you remember using what I just talked about, that is that the dot product works, because if you think that if gamma is constant, if the magnitude of gamma is constant, well, that means that we can also assume that the gamma prime, the gamma squared. If the magnitude of gamma is constant, then of course the magnitude squared is constant. Let's call it k. And now just rewrite this as gamma dot gamma. That gives you the magnitude of gamma squared. So that's constant. So now use a classical thing we did in Calc 1, in first calculus. What is the derivative of a constant function? It should be 0. So if you take the derivative of this side, you get something, the derivative of a constant vector. I'm going to write it like this for now. Sorry for mixing notations, but this guy is a 0 because it's a constant vector. And in this side, we use what we just noticed, that that's going to be gamma prime dot gamma plus gamma dot gamma prime, which is the same thing. So it's 2 times gamma prime dot gamma. So divide by 2, and you get that gamma prime dot gamma is 0, which is what we wanted, right? We wanted to prove that they're perpendicular. So if the gamma prime is not 0, then that means they're perpendicular. Okay, so that's something we'll use in a minute. And now let's talk about Kepler's laws. So Kepler's laws is saying that the orbit of a planet is elliptical with the sun at the focus. The second one is that during equal periods of time, a planet sweeps equal areas. And number 3, that the equal square of the period of one orbit is proportional to the cube of the length of the semi-major axis of the ellipse. So I'm not going to try to prove number 3 in these videos. I'm going to prove number 1 and 2 in these videos. I might have time to only prove number 1 in this video. I'll make another one probably for law number 2. So let's get into it. So we're going to assume from physics a few things. First, we're going to assume that the only effect that we see is everything in between two objects, the sun and the planet. We're going to use Newton's second law of motion. The force equals the mass times acceleration. And we're also going to use Newton's law, universal law of gravitation, which is the force between two planets is given between the difference of the masses. So here we think the big mass is the sun, the little mass is the m, and the r is the vector between them. And this u here is the unit vector. So u is the vector r. I'm going to use r here for position, so it's going to be r divided by the magnitude of r. So I'm writing it backwards. So the unit vector is going to be r divided by its magnitude. Okay. So, let's get into it. So we're going to assume from physics a few things. First, we're going to assume that the only effect that we see is everything in between two objects, the sun and the planet. We're going to use Newton's second law of motion. The force equals the mass times acceleration. And we're also going to use So we're going to use these two things. The big G here is the constant, universal constant of gravitation. Okay, so what we're going to do here is we're going to start proving something smaller. Our goal is to prove, number one, that the orbit of a planet is ellipse. But we're going to start with something smaller than that. We're going to start proving, to begin with, that the motion of the planet is on a plane. Okay, so we don't know even that. So once we know it's on a plane, then we can start from there that it's an ellipse. So to prove that it's on the plane, we're going to prove that the position vector cross the velocity vector is constant. That would make it be on a plane, because if we do this, then what we'll be proving is that, sorry, let me pretend we don't have this. So if I have that my curve position from a certain place, the curve follows this path, and at every position vector, r of t, the velocity vector here is going to be these tangent vectors, right? So for every point, every time you do this, you get r cross c, v, sorry. If it gives you the same vector c, then if you're getting always the same vector, then you can assume, oh, okay, so then this means that what was happening is that this was on the plane. Right? And the vector c is the normal to the plane. Okay, so that's going to be our goal, to prove that r cross v is constant. Okay. So let's go for that. So our goal is to prove, we want to prove that r cross v, and I'm going to prove that r cross v is constant, but it's the same. I'm going to try putting intervals for vectors. Sorry, it's going to be a little bit confusing. So if not, it's going to be confusing. So I want to prove that r cross v, the same idea as before. If it is constant, it means that its derivative is 0. Okay? If I prove that the derivative is 0, then we're done. R cross v is a constant. It's a vector, so it lies on a plane, the curve r. Okay, so how am I going to do this? Well, yeah, that's why I wanted to know that r cross v, oops, I wrote two crosses. R cross v derivative, I showed you these rules that follows a product rule. It's going to be r prime cross v plus r cross v prime. And all these are vectors. I forgot to put these. So I like that. So now, who is r prime? Well, r prime is a velocity vector. So here I really have v cross v plus r prime, r cross v prime. And v prime, the derivative of the velocity, is acceleration. So I have this. So what I changed here was I changed r prime for v, because that's the derivative of the position vector as a velocity, and I changed the velocity derivative by its acceleration. That's the definition of acceleration. So what we have so far is we didn't get too far, but we did get an expression for r cross v prime is r cross a. Okay? Okay. So now let's try to figure out a way to find r cross a. So I'm going to write something else. So here we have this. We have that the acceleration was, using Newton's second law. We have that the acceleration was negative gm over r squared, and then I had here the unit vector u, which I'm going to write the unit vector like r over the magnitude of r. So I really get that the acceleration vector is negative gm over magnitude of r cubed, unit vector. So I'm going to put here the r vector, correct? This is acceleration vector. But look what happens here. This means that a, the vector acceleration vector, is parallel to r. Right? This is what this says. Because it's a constant, this is a scalar factor, and it's constant. It's a scalar solid. It's not constant. The R could be changing in magnitude, but it could be stretching or compressing, but it's always in the same direction as R. So what did we have before? We had that R cross V was this, but A and R are parallel. So take the cross product of two parallel vectors and you get 0. So we're done. The derivative of R cross V is 0. So we're fine. Okay. We did prove what we wanted, and we put that this constant. Okay. So I'm going to stop here for the first part, and I'm going to make a second video for the continue with this.